Here we go. So we're into 4B.2, which is expressing linear transformations with matrix multiplication. Okay, it is a 3-part section, just like the other one was. So there's going to be a part 1, part 2, and part 3. We're only going to do part 1 today because I just felt like doing anything more would have been too much before the break. Does that make sense? So we're only doing part 1. All right. This is going to go on page 48 of your handy dandy notebook. So on page 48, we're doing part 1, which is the handout you got today. Writing linear transformations with matrix notation. What is our objective today? It is to rewrite linear transformations expressed as coordinate functions using what we call matrix notation. Okay. Before we do that, we're going to recap what we've been doing for the past 3 days. Are we ready for a recap? Okay. So during your do now, you should have did a peer check of your 4B.1 assignment. And hopefully you checked yourselves. Everyone should be on the same page. Yes. Because it's the purpose of a peer check. So the first question I'm asking you, what is the definition of a linear transformation?
Definition of a linear transformation.
Hit it, Max.
A linear transformation is something that follows the y equals x.
Okay, it follows the y equals x rule. Okay, I can see where you're going. Yes, but there's 2 main properties that we wrote down on our Freyer model.
Lines, not lines.
There we go.
A function from one vector space to another that respects the.
All you do is read your Freyer model. All you have to do is read your Freyer model.
I said that in my brain.
You just had to read, you said that in your brain. All right, according to your Freyer model, the key attributes are it's origin to origin, right? And lines to lines, okay? Which means that should there be any curves in there?
No.
No, there should not, okay? No, we're just recapping what we've already learned, okay? Examples of linear transformations. What were our examples? Huh? What kind of rotation though? About the origin. It has to be around the origin. What else? All about the origin. Reflection across y equals x. And what would you say? Dilation is about the origins. Y'all are so smart. Good job. Okay. You don't know? Y'all are so smart. Duh. All right.
Let me tell you what's not.
Next. What does a linear transformation look like when it's expressed as a coordinate function? There we go. Ax plus by, comma, cx plus dy. It's in that standard form, correct?
Correct.
All right, next review. Kind of like a review, but also just making a connection. What is the mathematical terms for A, B, C, and D in the linear transformation?
X, Y, Z.
Nope.
1, 2, 3.
They're coordinates.
Nope, not coordinates.
They're however where it moves.
Nope.
Can you give us a hint? What does it start with?
A C.
Coordinates.
No.
No.
Correlations.
Nope.
Complete.
Say it again.
Coefficient.
They are coefficients. These are called our coefficients. They're the numbers attached to the variable, right? So A, B, C, and D are our coefficients. That word is important leading forward today. Does that make sense? All right. Okay, so how do we feel about this? Do we feel confident in our review of what we've been doing for the past 3 days?
I don't think
Kind. All right. So today, what are we doing? We're going to be writing our linear transformations with matrix notation. Okay. We have 5 linear transformations that we're going to practice with. And they're the ones that we saw and looked throughout our notes. So they should look familiar from your notes and from your assignment. And then we're going to go from there. So we're not going to leave the last column blank. We're going to do the first 2 together. And I'm going to have you do the last 3 on your own. Got it? All right. So first thing first, writing as a coordinate function. When you're writing as a coordinate function, that means that you're writing it in standard form. That means even if it's not present, you're going to write it using 0 in its place. Does that make sense? So that's the first thing we're going to do here is write these in standard form. So first we have 3x plus 2y, comma, 4x plus 0y. Are we confident in writing it in standard form? In coordinate function form?
That's it?
Yes.
Oh, yeah.
Okay. Now, the new part is writing this as a matrix. Okay. the purpose of a matrix is to basically eliminate your variables, okay? Does that make sense? So that you're only focusing on your coefficients. We're gonna be eliminating the variables. So how does that look like? You're gonna be creating two matrices. We're gonna create a matrix with our coefficients and then a matrix of our variables. So to make the matrix, I'm gonna make a bracket. In my first matrix, it's going to have our coefficients only. So the coefficients here are what? 3, 2, 4, and 0. Okay. Your first row are the coefficients from your x term, not your first coordinate, and then your second row are the coefficients from your second coordinate. Okay, and then the variables that we're describing are x and y. Big.
That's so hard.
How do we feel? Okay, now let's do another one, and then you're on your own. So here it says we have negative y, comma 2x plus y. Writing it as coordinate function form, what does that look like?
-1.
I need 0 minus y, and then 2x plus y.
Okay,
You have to stay in the ax plus by order, okay?
0, 1,
What kind of one though?
negative
-1, then,
2, 1. 2, 1, that's not 4, that's 1.
and then our variables are
X, Y.
our x and y. Ta-da!
That was so hard.
That is today's lesson. So what you're gonna do is you're gonna finish up the table and check with your peers, and then we will come back.
The hard one.
We're gonna, what you're gonna do is finish up the table and check with your peers. Okay?
You do that on purpose.
You had practice already doing this if you did your assignment.
The easy one. I did do my assignment.
Okay,
And it's in the box on time.
good job.
And that's
Retirement.
All right, here we go.
0x, comma.
So before we can
-5.
write it in coordinate function, we need to simplify here, right? So we distribute. And you get negative y plus,
That is 0x.
-1 plus 1, comma, -3x. What happens to the ones?
They cancel each other out.
They cancel each other out. And I'm left with negative y, comma, -3x. So in coordinate function form, that gives me
0x. -5. -3x. -0. 0.
so then my matrix is
0.
we did good. All right, this one, I have no y's.
So
So
it'd be 3x, comma,
plus 0y.
yep, plus 0y, that,
Comma 2x's.
yep.
there we go. So my matrix looks like 3, 0, 2, 0,
That looks like 30, 20.
x, y. Yes?
My favorite.
All right, last one. So we had a little bit more work to do, right? Distribute. So you're left with 2x plus 2y minus 3x, comma, distribute, 4x plus 8y minus y. Yes? Now we're combining. What does 2 minus 3x make? 2y minus x. What does 8y and negative y make? A 7y, right? All right. So when I write it in this form, I have negative x plus 2y, comma, 4x plus 7y. So we have -1, 2, 4, 7, and our variables are x and y. How we do?
I did great.
Did we do good? All right, so after Thanksgiving break, we're going to talk about how are we going to be using the matrix transformations to solve. Got
I
it?
want to talk about after this.
All right.
I want to be on this.
Good job, guys.
Oh my goodness, I have to go.